All right, so in this lesson, what we're going to do is we're going to run this gradient descent without SymPy. We're going to look at making our Jupyter Notebook a little bit more performant. This gives us a chance to solve this problem the old-fashioned way, the way we've done it for the previous examples. And one reason to do this is that you'll notice this performance difference in your Jupyter Notebook, because it turns out running it without SymPy is actually much faster. But first, let's add the markdown for our partial derivatives in LaTeX notation. So I'm going to go back to this section heading here, and we're going to write down the partial derivatives in mathematical notation, because it'll give us a good opportunity to see a few more of these LaTeX tags in action. In our print statement, on the cell below, we've got the partial derivative with respect to x, and it looks like this. So the question is, how do we translate this very little bit ugly and unreadable equation into LaTeX notation? The first thing I'm going to do is use the opening double dollar sign tags. And I'm going to have a little fraction here. I'm going to say backslash frac open curly braces f closing curly braces opening curly braces x closing curly braces, and then two more dollar signs. Let's see what this looks like. So we can see that our fraction tag and the dollar signs together center our equation like this. So let's take a look at this. Let's make it a bit bigger. I'm going to add the 2 pound symbols before this thing and press Shift Enter again so we can see it a bit larger. Now I'm going to add the mathematical notation for the partial derivatives. So I can go back into my fraction and use the backslash again, and before the f, I'm going to use a tag called partial and have a space, and you can see that the markdown actually highlights this tag differently, highlights it in green, just like it does with the fraction tag. So that way I know, just from the syntax highlighting, that this is a legitimate LaTeX tag. I'm going to also add the partial tag to the bottom. So I'm going to say backslash partial space x, and then after the curly braces, I'm going to put an equal sign. And I'm going to press Shift Enter and see what it looks like. And here we go. Here we can see the partial tag translates into these little delta symbols for the equation. Okay, so now we can add the top part of the fraction on the right-hand side. And that was 2x, and then we had log. I'm going to use the natural log here. So backslash ln, and it was 3 times 3 to the power of, and then curly braces, minus x to the power of 2 minus y to the power of 2, closing curly braces. Let's see what this looks like. Now one thing I don't like is this times symbol that we've got here. It would be much nicer to have a dot, and there is a LaTeX tag for that as well, and it's backslash c dot. Pressing Shift Enter, we can see that it now looks like this, which is a lot nicer. So we've got our top part of a fraction now. Now all I have to do is actually, well, now all I have to do is actually put it in a fraction. So I'm going to say backslash frac, open curly braces, and at the end, closing curly braces. And then I'm going to open another pair of curly braces at the end. This is going to be for the bottom part of our fraction. Now at the bottom, we had 3 to the power of, and then it was curly braces minus x to the power of 2 minus y to the power of 2, closing curly brace, plus 1. Let's press Shift Enter and see what this looks like. So now our equation looks like that. We've got a fraction, we've got the top part, and we've got the bottom part. But this isn't quite correct. We have to add a little bit more notation since the bottom is actually squared. So how do we do that? One of the things I can do is I can take a parentheses here and a parentheses at the end, and then have that whole thing to the power of 2. And pressing Shift Enter, it would then look like this. I have the parentheses and then the 2 like so. And you know, the thing is, this isn't even all that terrible, but I can use LaTeX notation again to style these parentheses a little differently. So instead of having just a normal parentheses here, I can actually have a backslash and say left parentheses. So this is one of the tags. And then at the end here, instead of having the closing parentheses, I can actually also put backslash right and then have the closing parentheses like so. So this code here, this markdown, now refers to the right or closing parentheses. Let me press Shift Enter to show what this looks like in comparison. You can see now with the left parentheses and right parentheses using the LaTeX tags, it actually looks a lot better. And just like that, we're done. We've got our partial derivative with respect to x formatted very beautifully in LaTeX notation. Let's add the partial derivative with respect to y now. So this is the really easy part, because all we have to do is copy this, paste it, and change this x to a y, and change this x to a y, and press Shift Enter. Now we've got both our partial derivatives displayed here. Now, if you're suspicious and you don't believe me that this is indeed the partial derivative for y, then you can go down here and you can refresh this cell here just by changing this a here, where we're calling the differentiation function from simpy to b and hitting Shift Enter. And then you should be able to confirm that this indeed is the partial derivative with respect to y. So now that we've figured out the functional form for both of these partial derivatives, can you, as a challenge, can you write these partial derivative functions as Python functions? Now I'll also give you a hint. When you're writing the Python functions, there's actually one additional requirement that you have to consider. Also, for the function names, use the names fpx and fpy for the names of the partial derivative functions. I'll give you a few seconds to pause the video and give this a shot. All right, you ready? Here's the solution. For the solution, I'm going to add a little Python comment, and I'll just say partial derivative functions example 4. And here they are. It's going to be def fpx, which needs 2 inputs, an x and a y, colon. And to write the partial derivative for this, I'm going to, again, use a little simplification. I'm going to define a variable called r, and that's going to be equal to part of my expression. I'm going to have 3 to the power of minus x squared minus y squared. So then my derivative is going to be 2 times x times log 3 times r. This is the top part. And the bottom part of that fraction is going to be r plus 1 squared. And that's it. That's my partial derivative with respect to x. And as we've already discussed, this is very, very similar to the partial derivative with respect to y. So I'm just going to copy this and change this to y and change this x in my return statement to y as well. Now, I said there was one requirement that you have to take into account, and this is the log function here. This comes from the math library, the math module, and we have to import this functionality in our Python notebook for it to work. Otherwise, when it comes to running fpx or fpy to evaluate one of these functions, you're actually going to get an error. So if I had fpx and at 1.8 and 1.0, and I hit Shift Enter on this cell, I'm actually going to get an error. And the reason is that log is not defined. I can't just use the log functionality like I would up here without importing the module first. So let me go back up to the very, very top. And then down here, I'm going to say from math import log. Then I'm going to hit Shift Enter on this, and I can scroll back down again, and I can try rerunning this cell here. And I can see that my slope, my partial derivative with respect to x, is equal to 0.037, which is exactly what I am getting here. In this case, I'm using SymPy to evaluate my partial derivative. And in this case, I've already got my partial derivative here as a function, and I can just plug in the values. So one question you might ask is, well, why did you use log? Why is this not ln? And the answer is that if I check the documentation on this, then you see here, if I hit that little plus sign, that if the base is not specified, so if there's no second argument being passed to this function, it returns the natural logarithm, so ln, base e of x. So in fact, this log 3 is the natural logarithm, or ln, which is what we've got up here for our partial derivative function in the LaTeX notation. So now we've got that out of the way, we can do a bit of a horse race between these two methodologies. We can namely take this cell here, and we're going to copy it. We're going to copy this cell, and what we're going to do is we're going to paste that cell here. I don't need this one. I'm going to delete that. So I'm going to go to Edit, Delete Cells, and then I'm going to modify this cell. In particular, I'm going to modify these two parts to use my fpx and my fpy functions instead. You know what? Maybe you should give this a quick shot. See if you can figure out what code should go here in order to use fpx and fpy, the partial derivative functions, instead of what we had before. I'll let you pause the video and I'll show you how to do it in a second. All good? Here's the solution. You simply call the two functions and supply the x value and the y values. So the x value was under params square bracket 0, and the y value was under params square bracket 1. And that's it. That's the gradient, or partial derivative with respect to x. And for our gradient in the y direction, we do exactly the same thing with one difference. We're going to use fpy, the partial derivative with respect to y, and we're going to supply the same two inputs, the first value in our array and the second value in our array. Now I'm going to run the cell with 500 iterations and see how well it performs. Ready, steady, go. And it's done. Going back up here to where we're using SymPy, I can change the maximum number of iterations to 500 and rerun the cell. Thinking, there we go. So you can see that Python is actually doing a lot of extra work in this case. Every single time this loop runs, it has to differentiate our cost function and then evaluate that cost function. And these instructions actually are a little bit more resource intensive than if it already knew from the get-go what the partial derivative was. And this is one of the drawbacks of why you might not want to use SymPy in your loop if you're running an optimization algorithm many times. So yeah, I hope you enjoyed that. So I really think this was an interesting exercise because it really shows some of the pros and cons of the different tools that are at our disposal. On one hand, SymPy can make our life a lot easier when it comes to calculating derivatives and doing symbolic mathematics and much, much more. But on the other hand, it does show that you have to be clever when it comes to running your optimization algorithm. You do have to think about a little bit about the resources that you're using in running your optimization. And this kind of goes back to thinking like an engineer, thinking about the resources that are at your disposal and how you can write your code and how you can choose your algorithm to make the most use of the resources that you have. Okay, so what's left to do? Well, only one thing, right? Plotting the gradient descent on our wonderful 3D chart. And this is what we're going to do next lesson. So I've still got that coffee pumping through my veins, so I hope I'll see you there.